Hey folks, this is Captain Jones here to talk to you about subroutines, which are little function calls that we can make in our LC3 programs. There are a couple of ways in which the LC3 directly supports that. So today we're going to talk about the LC3 instructions that allow for procedure or function calling and what effect on the processor those instructions have. We're going to show you how to write programs that can call subroutines or be called as subroutines. And then we're going to show you how you can trace these programs in the simulator to understand kind of what they're doing. So let's get started. Okay, so without subroutines, anytime we want our program to do anything, we have to embed it directly in the code. So you can see this diagram here. We've got functions X, Y, Z, W that all do stuff, and a function called A, which does something incredibly useful. So useful, in fact, that we want to do that thing multiple times in our code. Without subroutines, we have to place the actual instructions in memory every time we want this function to do something. And there are two problems with that. One, we might find that the function A takes up a lot of our memory space. Every time we need to call it, we need to put it into our memory. And two, this would be terrible to maintain. Anytime we make a change to one version of program A, we have to make that change everywhere in the rest of our code where A is, and so that can is a easy, quick recipe for for there to be versions of A that don't match up with each other. What we want to be able to do is write A once and be able to sort of call that function from multiple places in our code. So A would live in our memory in one location. Whenever we wanted to invoke then we would somehow sort of tell our program, okay, after X finishes, then call A and come back. After Y finishes, call A again and then come back. After Z finishes, call A third time and then come back. And so then not only is A in our memory only once, if we make a change to A, there's only one place to make that change, and all of these call sites, get that update effectively because they're referencing this version of A. And so this makes for great code reuse, and there's lots of benefits. We can already branch around, but the trouble with doing this, efficiently is that in order to return, we might be returning to different places in our code. So we need some way to sort of record when A finishes where it's going back to. Is it going back to the start of Y? Is it going back to the start of Z or W? So to do that, we're going to co-opt R7. R7 is going to become the place where we store the value that A should be going back to, and so we call that the return address, and we'll refer to R7 as the link register because it's the register that links this subroutine back to the calling code. And so before each call to A, we'll place the starting address of Y or Z or W in R7, and when A finishes, it'll jump to the correct location in code. So we could do that again with a branch instruction. It would require some micromanagement, but this is such a useful feature. We actually have an instruction dedicated exactly for this called JSR, which stands for Jump to Service Routine. It comes in two flavors, JSR and JSRR. The difference being, are we specifying the function the subroutine we're trying to jump to by name, or by offset from the program counter, or are we jumping to that service routine and its starting address is located in a register? So JSR you could think of as jump service routine, JSRR you could think of jump service routine register. In both cases, the processor, when it executes this instruction, it's going to automatically store the program counter in R7, our link register. And recall that the program counter is incremented on the very first step of the fetch cycle. So the value in the program counter when we store this is the address of whatever instruction is coming after JSR or JSRR. And then the processor will execute an unconditional branch to one of these locations. If it's JSRR, it's going to execute a jump to the address that's stored in this base register. If it's JSR, then the processor will execute a jump to the value of the program counter plus whatever 11-bit offset is specified in the lower portion of the JSR instruction. Cool. So we can use the JSR, JSRR to jump around to service routines. And we'll see kind of an example of being able to use that here to sort of turn our multiplication program into its own little function. But before we do that, there's two things we need to talk about that are important about calling subroutines. And the first is, when we're in something like function A, you know, function A might need to use certain registers. Our multiplication instruction uses registers to sort of to accumulate values or to subtract values, and our goal when we call our subroutine is that when we return to y, if we make this call to a in between x and y, and then we return to y after a is finished, there shouldn't be registers that get lost or stomped on. So we have to specify what are called call saved registers and call saved registers. And the delineation is based on kind of which part of the program has the knowledge of which register might be in use. So the calling functions. Here's an example of program X calling subroutine A. So in this case, X is calling A. X knows that the JSR instruction is going to place the program counter in R7. So this is called R7 is called the caller saved register. And if X were using R7 for whatever reason, then it would be the responsibility of the caller of X to store R7 somewhere safe, so that when the jump service routine instruction is called, R7 can get the program counter and the value that was there is not lost. So you see here, kind of step 1 is to save that caller register if we're using it, and step 5 is to restore that value if we need it again. So we'll start to build up here. Let's say this example, we're trying to multiply two values. We're going to load those values here. In this case, we're not using R7, but if we were before and after the jump service routine instruction, we would save and restore that. Any other registers that are used by the subroutine are called callee saved registers, and the subroutine has to save them itself. And the reason is simple. It's because ideally A, the function, is sort of a black box, meaning X doesn't know exactly how it's doing its work. It just knows how to call it, and so it has no idea which registers A uses in the processing of its function. And so if subroutine A needs to use any registers, what it has to do before it does anything with them is save them somewhere. And before it returns, it needs to sort of restore those registers back to their proper location. So you can see that down here in our multiplication function. What we're going to do is use R2 as our accumulator to accumulate the gradual sum of our two values, and we're also going to gradually decrement R1, and just to adhere to this concept that we want the subroutine to finish and try to leave everything in as close to the exact state as it was when it was called. We're going to store R1 so that we can restore it later on after we've decremented it. So you can see here in this subroutine, we are saving two registers, R1 and R2, because this subroutine is changing those in the processing of that subroutine. So one piece of housekeeping is we have to delineate what are the caller and callee saved registers, and these two functions need to make sure that if those registers are being used, that they're being saved somewhere beforehand. So you can see the mechanics here. I've got two places in memory, save R1, save R2, where these two values are going. And this is a great example of using the block word assembler directive. I'm telling the assembler, okay, I need one spot in memory for R1 every time this function is called. But of course, that value is going to change every time. So reserve one empty place in memory, and I'll use the store instruction here to fill it every time the subroutine is called. Okay, the second piece of housekeeping, and the last one we need to talk about, is something called the application binary interface, which is a heavy word for how do X and A talk to each other. So if in this case my multiplication routine is multiplying two values, okay, where is it going to find those two values when it's being called, and on the backside, where does this the calling function, where does it find the result once the subroutine is finished? And so I probably should have commented it in here. The assumption is that when this function is called, the two values being multiplied are stored in R0 and R1. So you can see here, prior to me calling this function, I load R0 and R1 with my values, and then this program this subroutine is going to assume that those values don't necessarily need to be kept, and so when it is finished with its multiplication, here you can see this here, it's going to take the value that is in R2, that's the result of the multiplication, and it's going to store it in R0. So the assumption is that R0 and R1 contain the multiplier and the multiplicand. If I got that right, I think the two values that are being multiplied together. And when the subroutine is finished multiplying, R1 will be unchanged, but R0 will have the result of that multiplication. And so that's an important part that needs to be communicated, between these two here, the caller and the callee. And you can see that in sort of the process of calling this function. After we save our caller registers, after we save R7 if we're using it, then we have to make sure that our arguments are in the correct spot. R0 and R1 are pretty typical, but there might be elsewhere where these arguments need to be placed. And then after we make our subroutine call, then we sort of retrieve our return values. In this example here, the return value is stored in R0, which means, whatever we wanted to do with that multiplication here, we get it in R0. And then similarly for our subroutine, once after it saves the callee registers and it does its whatever it needs to do, it's going to restore any registers that it stomped on, and the last thing it's going to do before it returns is place its return value in the register that was specified by the interface. So that's those are these two instructions here. And then lastly, the subroutine issues the return instruction, which is it's not an instruction itself, it's a mnemonic that is shorthand for jump R7. So what we're telling the processor to do at that point is get the value out of R7, get the address of the instruction that was just following JSR, and then jump there. Okay, so let's see this in action. If I go to my simulator and sort of reset everything, I can step over my two load instructions. So R0 and R1 have the values 8 and 7. Those are the two that I want to multiply together. And I want to execute this service routine. So if I hit step over, what I'm telling the processor to do is run that whole service routine and go to the next instruction. So the result of multiplying 8 by 7 is placed in R0, and my processor at this point is ready to halt. That's a great example of what the step over button does. But let's say I actually wanted to see what that function is doing. So I'm going to step over. When I get to my jump service routine instruction, I'm going to step into that service routine. And you can see here now, this is my service routine. First thing I'm going to do is save R1 and save R2. So you can see here, R1, the value 7 was saved in memory. R2, which happened to be 0, it was saved in memory. I'm not really using it in the parent program, but because I do in the subroutine, I have to assume that it might be used, and I have to save that anyways. And so now what I can do is, clear R2 and start using that to accumulate my multiplication. So I'm going to, add R0 to R2, decrement R1, and then continue that loop until I set a breakpoint here and run that until I'm finished with my multiplication. So R1 has been fully decremented. The results of that multiplication is here in R2. So the last thing I need to do is clear R1 and store the result there. So 56 is the result of that multiplication, goes in R0, and restore R1 and R2. So 7 was put back in R1 and 0 is placed in R2. And then I execute this return instruction, which is going to jump me back to the parent program which in the next instruction is a halt. And actually, you know what I want to do is show you very quickly that right before I execute this return instruction, R7 has the value 3003. That's the memory address that was right after our jump service routine instruction. So again, return is, loads this into the program counter. When I step into that, then my program counter goes to 3003. One other use that I don't think the simulator supports, but the textbook talks about it, is why we might use JSRR. So if we have, for instance, a function here, let's say A is written in a different file, and I can't necessarily refer to it as an offset from the program counter. What I might do is just sort of add some lines to my assembly code that sort of I tell the assembler, hey, this thing A is defined externally. It's defined in a different file, and and so what I want you to do is get the address of that eventually, and we'll load that here into R4 and issue this jump service routine register instruction to get to R4 as sort of a indirect way of accessing this function, which is defined in a separate file. And if we've written our assembler and our linker correctly, then before this is combined into an executable, the linker will have a copy of the that function A, and it can sort of fill in the values that it needs to here for this function to be able to call that. Okay, so to summarize really quickly, subroutines are exceedingly useful. They keep our memory footprint small by letting us reuse our code and keep any changes that need to occur in a single spot. To jump or call that subroutine and then come back, we kind of already know how to do that. We can branch around, but in order to make sure that we come back to the correct spot, since we might call this function from anywhere in our code, we need to use the link register R7 to store that. The address of where we're returning, and that's such a useful thing. We have an instruction dedicated to just doing that. JSR is jump service routine, so that when we execute this instruction, we'll automatically store the program counter into R7 and then jump to either the base register or some offset. When we're writing our code, there's two housekeeping rules we need to keep in mind, and that is that if we're calling a function and we're using R7, we need to save that value because it's going to get overwritten when we issue our jump service routine instruction. And if we're writing a subroutine, then any registers we use, we need to save because they are potentially being used by the calling program. So that's housekeeping number one. Number two, we need to sort of keep define for these for the subroutine where its arguments are to be placed, which registers it can find them in, and where it's going to place the return value. So I probably should have added that as a comment here, but the assumption was that with this function that if I'm multiplying two values, those two values will be located in R0 and R1, and the result of the multiplication will be stored back in R0 at the end of the function. And I can even if the simulator supported it, I can even do that with functions across multiple files. All right, that's all for today. I'll see y'all next time.